Today, Brett's going to talk about trajectory-aware eligibility traces. Brett is a PhD student here in the department. He's wrapping up his first year-ish because he's came from a different program. So he's kind of cheating, and he's not really a first-year PhD student. So this is a paper that we had accepted by STEM this year. So take it away, Brett.
Cool. Thanks, Marlos. So I'm going to be talking about trajectory-aware eligibility traces for off-policy reinforcement learning. And yeah, so thanks for coming, everyone. And let's get started. So a quick outline of my presentation. And you know, we lost a little time due to the mic issues, so I'll try to do this quickly in the beginning. But I think like it's worth just first of all going over what are off-policy eligibility traces in case people don't know, because otherwise the trajectory-aware part won't really make sense. So I'm going to cover sort of previous methods and then maybe some shortcomings of them and why we felt like we wanted to write this paper. And then talk about some of the benefits, theory, and implementation of these so-called trajectory-aware methods. And then at the very end, we have an algorithm called recency-bounded importance sampling, which demonstrates one practical possibility of this theory and some interesting experiment results that we got. So first, some background. So just we're just here in the standard Markov decision process setting. So we assume that we have an agent interacting with its environment. There's a set of possible states and actions. And then every time the agent takes an action, it's going to stochastically modify the state of the environment. And it will receive some reward, positive or negative. It could be good or bad. And that's going to be the only feedback that the agent is receiving on its performance. So the key here is that the policy itself is stochastic. So this is, even when the environment is deterministic, this is an inherently noisy process. And so we're going to need to interact with the environment a lot to obtain sample averages and learn sort of the outcome of this policy. And in this setting, we're also going to just assume that this is episodic, meaning that there will be some finite number L eventually. We're in states, we're taking actions. Eventually, this process will terminate. Okay, so the prediction problem is really the main focus here, because if we can do prediction, we can also control our environment. So I'm going to spend most of the time talking about prediction today. So here we have a value function, which is really a vector of estimates for all the states we have. We're just going to assume no function approximation for right now. And our goal is to estimate from each possible state we could start in, what is the long-term cumulative reward that we will receive an expectation under our policy. And we also have a discount factor of gamma, which is going to decay the relative importance of rewards. And we just assume that that's going to be fixed for our problem. Yeah. So that's our goal, is to estimate this quantity. It's obviously unknown, so we need to interact with the environment. And ideally, we want to do this with as few samples as possible, because that means we're learning more efficiently. And then all of the algorithms I'm going to consider here are some form of temporal difference learning. So probably most people are familiar with this, but again, just to recap, the way TD learning works is we track a moving estimate of something. In this case, we're going to be doing predictions of return. And we do this by just mixing a small amount of a new estimate with our old moving estimate in sort of this exponential average way. And so this new minus old is our temporal difference. And just by accumulating these temporal differences, we can actually eventually learn very long-term outcomes and converge to the correct prediction. So that's very interesting. In the case of reinforcement learning, our old prediction is just whatever our value estimate is for this state that we're in, ST. And the new prediction is going to be based on the reward and then discounted value of the next state that we end up in. And that's where this concept of a TD error comes from, which we're going to denote as a lowercase delta. But just by interacting with the environment and adding these TD errors with alpha, which is just a small coefficient, less than 1, we will eventually converge to V pi, which is the quantity, the expected discounted return we want to estimate. So that's pretty cool, but it's not necessarily fast, because what it means is we're only getting a small update on each time step. And we'd like to do better than that. We have this whole trajectory of experience, and we're getting a TD error on each time step. So we'd like to combine these and get a larger update to our value function. And one way we can do this is with TD lambda, which is and this is sort of the theoretical view of TD lambda. So we're looking into the future, and if we were going to take these TD errors that we experience, we can combine them in this exponentially decaying way. And in reality, you could, there are lots of different weightings that you could put on the TD errors. But one reason we like exponential decay is that it's just very efficient. It's easy to implement. And it also has this recency heuristic assumption. So it's actually sort of encoding this bias in the agent to say that the farther into the future that these TD errors occur from the event that we're assigning credit to, we actually want those estimates to be weighted less. We actually trust them less. They're noisier, just because of the variance of the problem. The more steps you look into the future, the noisier it gets. And so we eventually just sort of want to stop assigning credit based on what happens, because it's just so disconnected from whatever this current state is. So lambda is this trade-off parameter. It's that we can look farther into the future. Lambda is between 0 and 1, by the way. I forget if I mentioned that, but that's why it's an exponential decay. So we can either look very immediate short term, but that will probably be slow, or we can look very, very far in the future, which will be extremely noisy. So in practice, we want somewhere between those values. And just to sort of illustrate like what happens when lambda is 1, if you take 2 TD errors and you add them together, one of them discounted, they actually have this neat telescoping property where some of the value estimates will cancel. And what you get is effectively a 2-step TD error. So this is like analogous to the delta that we saw before, but we're now using 2 rewards and then subtracting our value. And if we just kept doing this inductively, we just keep adding discounted TD errors all the way to the end of the episode, we would actually just end up with this Monte Carlo return subtracted by our value. So this would be a form of estimation where you execute some rollout, you observe the return, but each reward itself is a random variable. So this would be extremely noisy. That's why we don't want to do that. And then so, yeah, in practice, this lambda is giving us something in between this high bias TD update and this very high variance Monte Carlo update. And so usually, almost always, in my experience, TD lambda will just perform better because it's just more favorably trading off this bias and variance. And then, yeah, I included this slide because my title has eligibility traces in it, but we're going to be talking less about the sort of practical implementation today and more about the theory. But just to give you an idea of like what I meant when exponential decay is nice, is because we can track how long it's been since we've visited a certain state by using this extra vector called an eligibility trace, and we denote that with this Z. And what we really do is whenever we visit a state, we increment this value by 1. And then on each time step, we're going to decay this by a factor of gamma lambda. And so this is kind of a neat way of remembering, remembering this coefficient here for every possible state in parallel. And what that means is that we can apply these TD errors as they're coming in one at a time. We don't have to wait. Like if you look at this equation, it seems weirdly theoretical where you have to wait an infinite amount of time until at least the episode terminates to apply the update. But eligibility traces would be how you actually implement this in a smooth, temporally continuous way. So it's pretty neat. Like I think the focus of my talk is going to be more on like sort of you'll see, but kind of like variable lambda in a sense, like what happens when we want to do fancier things in terms of this bias variance trade-off. So the eligibility traces are not too important today, but they are very useful for the implementation of these algorithms. Okay, let me just quickly check the time here. Okay. All right. So yeah, quick. Another few things that I just need to introduce. We're doing off-policy prediction. That's actually what the focus of our paper is. So it starts getting a little more complicated, but we actually have 2 policies. We have some policy mu that this is what we're actually sampling from the environment. But usually we want to make predictions about a different policy. Maybe we're exploring, but we actually want to learn about the optimal policy. Or we could have options and we're executing one, but we want to be simultaneously learning about possible other options. So this is extremely common in reinforcement learning is this kind of double policy problem. They call it off policy. And the traditional way you do this is by using importance sampling, because we're sampling from this distribution induced by our behavior policy mu, but we actually want the one induced by pi. So we have to multiply it by this factor of rho, which is correcting the probability. It's, this pi divided by mu term. So this becomes problematic. Okay, one second. So this will become problematic because we're going to be multiplying by these rows, which could be very large. Like they aren't bounded by 1 anymore, like lambda was. So they can actually like grow exponentially and just create like a massive variance in your problem. It'll be hard to learn. So even though it's correcting the expectation, the variance will be so high that it's like just almost impossible to get these to work in practice. So sorry, one more preliminary thing is just for the ease of introduction, I was using this V for value estimate, but we can learn about state action pairs too. And so we're going to just quickly substitute instead of V, we're going to use Q, and we want to learn about the value of a state action pair. So pretty much everything I just said is the same, but now we're just going to be learning about not just the value of a state, but also the value of a state given that I took some action in it. But then everything else, like the TD update rule, is very analogous. The difference is that we can define V in terms of the expected value of Q. This comes from the Bellman equation. And so our TD error, we're going to denote it with this little pi superscript. But conceptually, it's going to be very similar. So sorry, just had to get that out of the way. But it's a lot easier to talk about TD lambda and things when you use V. So that's why I did this quick substitution. So like I said, so off policy Q lambda, we're going to be multiplying by this product of rows. And this is going to correct for the expected value of the update. And so this looks almost exactly like the TD lambda update rule, but we're using Q values now, and we're multiplying by this product of row. But like I said, the variance can be very high, so that's a problem. So what recent work has done, like 2016 probably, is this is the retrace paper, like Munoz et al. 2016. I don't have the citation here, I'm sorry. But what you can do is you can generalize this Q lambda update to use pretty much any value less than that row on that time step. So it's going to create bias. You're sort of down weighting these TD errors. And so you're considering less of the future, essentially. But that's significantly reducing variance. And what this paper proved is that as long as your coefficient C is always less than rho, like it doesn't matter what it is, it could be random numbers, essentially, it will still converge. So that's pretty neat. A few algorithms that do this, like one in particular I want to note is retrace, which really is essentially Q lambda, but it's clipping the row on each time step. And this is an interesting effect because, like I said, one of the problems is that when rho is greater than 1, it could explode exponentially. So by clipping it, you've completely stopped that problem from occurring. And so it really helps with variance, and retrace is a pretty effective algorithm. It was probably the best baseline when we started this work. All right, cool. So awesome. So now we can start getting into my research that I did with Marlos and Martha. So we're going to generalize this update further, and we're going to replace this product of these arbitrary C values with just a single value that we call beta. And in general, beta will depend on the full trajectory up from, the time that I took that state action pair until this TD error arrives. So that's from time T to T plus K. It's very abstract, I know, but we can break this down a little. So one way to think about this is that rather than having to multiply these different values like we usually do with an eligibility trace, we're actually just considering the most general case where we just use one number to represent that product. And that means we can do things that, like, we don't have to be accumulating these products together. We can have like very interesting algorithms, which I'll explain in a little bit. But another way to think of this is that we have, in sort of a neuroscience sort of vein, we have this eligibility trace that has a hysteresis ability, which means that its current output is dependent on the past. So like in a standard eligibility trace, you have this very simple spike and decay model where like you achieve some stimulus and it causes this eligibility spike. And then this exponential decay is sort of the effective window that neuron is eligible for reinforcement. And this beta is, in a way, generalizing it so we can consider more complex models, because not that necessarily I was trying to do this for my paper to model real neurons, but the real biological systems are much more complex and have that hysteretic ability. So that's somewhat interesting, like we're really considering the most general possible case of eligibility traces here. But in my case, I was more interested in sort of the practical, like, sample efficiency of these methods. And one last note is that although this framework seems abstract, like you have this beta function, it's taking a whole trajectory as an argument, it doesn't mean that the agent has to actually memorize this trajectory necessarily. It could maybe just use the last two state action pairs and ignore the rest, or it could be implicitly dependent on it. Like you have two different traces and you're combining them in some way mathematically, and that would technically be dependent on all the past inputs, but it doesn't have to just remember this trajectory. So yeah, so quite abstract so far. So I can hopefully make this a little more concrete. And I think I think I actually covered like most of these points already, so I'll probably skip this slide, but we really want to do this mainly for better credit assignment decisions. And this could also be really useful when we have either episodic tasks or we're using experience replay. So we have like these trajectories available and we can do smarter credit assignment. We don't have to experience TD errors one at a time. But then on the theoretical side, it's interesting because we can also unify all of these past algorithms in one expression. So anything we prove about these trajectory aware traces carries back to pretty much all of the previous work. So let me give an example of why we think trajectory awareness and kind of product of all of these, you would just get a value of 1. And so what that's saying is that actually, oh, unstable. Sorry about that. What that's saying is basically like this state action pair was actually important under the target policy. Like we should reinforce this. But if you use something like retrace, which is always clipping these row values, all the 2s will become 1s. And when you take this product, it's actually going to decay by like 1/2 and then 1/4 and then 1/8. And, you know, in this case, just a very short sequence, it's already below like 0.1, 1/16. So you can have these interesting cases where you're actually experiencing very rare and important trajectories under the target policy. And using per decision traces, we're not remembering that we already cut these traces and controlled the variance. So we're just like, we're not assigning, in a sense, the proper credit that these trajectories should be, you know, should be attributed. And so like the takeaway here is that it's really hard to limit the variance of the problem, but also preserve these long-term, you know, credit trajectories when you're just using per decision, because you can't remember that you've already been clipping these traces in the past.
Sorry, quick question. So by cut, you mean flipping, right?
Yeah, so by cut, thank you for asking that. So the also, if people online can't hear, the question was, what does it mean when you cut a trace? Does that mean that you're clipping? And what we mean is that basically whenever we have one of these C values and it's less than the row on that time step, that's considered like a partial cut of the trace. So we're talking about relative to the importance sampling estimator, which would be the maximum trace we could have. If we have anything more than that, you can actually start to experience divergence. Yeah, great question. Thank you. So, so some example algorithms, like another reason we wanted to explore this is like people already do these trajectory aware methods. They just might not call it that or express it in this sort of formal language. But one thing that I've seen in a few papers is people will just take a trajectory and they'll just compute all of the important samples for that whole trajectory, and then they'll just cut them to 1. And then they'll just use that in the update. And that sounds like it would be a good idea because like you're only making the importance sample like less, like smaller. And so it seems like that should be like well behaved. And one of the theoretical results we found in our paper was that that can actually cause problems, which is like very surprising. Sorry, one thing, check time. So, okay, just trying to make sure that I finish everything on time. So I don't think I'll go over the other examples, but just one other takeaway here is that the way we can express old methods in this new notation is just by using beta as a product of those C values that we had before. So like with off policy Q lambda, this is most evident where beta is just the product of lambda and rho over that whole trajectory. So it's like strange and abstract to like represent it this way, but this is theoretically how you can unify these past per decision methods and these newer ones. Like if you look at this truncated IS, like this is a nonlinear function, this min of 1 and this row product. So you can't, there's no product of numbers that you can multiply to like get that value. All right, so that's enough of that, I think. So I'm not going to present too much convergence theory, but there was one thing that I did want to emphasize, which I think is pretty neat because it's very analogous to existing work in per decision traces. But when we have these beta values over a trajectory, if you guarantee, and this is just a sufficient condition, so this might not be necessary, but it is sufficient that if the ratio of your beta, like the change from one beta to another on a time step, as long as that's always less than or equal to rho on that time step, then you still will converge. So you can think of this as sort of like an effective trace, like kind of very analogous to the C in the per decision case. Like to give a concrete example, we look at off policy Q lambda again, and we divide the beta at time t plus k and t plus k minus 1, we just get exactly what the per decision trace would be. And of course, that's always less than rho because that's how we defined it. We're multiplying it by lambda. And that's why off policy Q lambda always converges. It doesn't matter what lambda is. So that's kind of neat. Like this new theory is explaining some of the old results. And like I said, it also can show that truncating the importance sampling when you just clip to 1 can cause divergence, which I don't show here. It's actually pretty complicated to show, but sort of the counterexample is, imagine you have an extremely large product of rows. So then your beta would be like clipped to 1. And then on the next time step, you get a very small row, but not small enough to make that product less than 1. You would get this ratio of 1 because it's just 1 divided by 1. But your row was very small, like we said, and less than 1. So like by counterexample, we've actually violated that condition. Which, like I said, that doesn't necessarily mean that it diverges, but it means that it doesn't satisfy this theorem. And we were then able to find a counterexample, like a sort of like a bandit problem where you can actually show that the expected update is not a contraction, so you can have this divergence. But yeah, I think like that's enough to be said in this talk. The paper has a lot more detail if people are interested. But yeah, like the takeaway here is that we have sort of this effective per decision trace. So even though the traces are trajectory aware, as long as the instantaneous ratio on this time step is less than rho, we know that will converge. And so that's a really useful convergence check. Cool. So we wanted to then finally use this theory and see like, is our hypothesis right? Like, can you actually get more sample efficient learning by doing trajectory awareness? So we came up with this algorithm called recency-bounded importance sampling. And it's very similar in a way to truncated IS, but we're truncating based on this exponential function, this lambda to the k power. So what we're basically saying, since we're, if this min function doesn't activate, like if you ignore the min of lambda k, we're really just taking our previous estimate and multiplying by rho, and we're just multiplying by rho again and again. So we're actually just doing importance sampling anytime we can. But as soon as that value exceeds this exponentially decaying upper bound, we clip it. And then we keep doing this. We multiply by rho. And so first of all, this is really easy to show that it converges because by definition, it cannot be greater than beta t minus like the previous beta times rho, like because it's one of the arguments of this min function. It just cannot be larger than it. So like already like convergence proof done, like it converges, it's sound, which is very nice. And then like kind of more intuitively, like why we want this is because when we're beneath that exponential upper bound, that means that the importance sampling product, this product of rows, is very small. And so that's something that we want to preserve as long as possible, because it's this low probability event under our under the target policy. So like this could, if we were just doing importance sampling, like we might ignore this trajectory, but we actually want to be, you know, like we can use the true importance sampling product without worrying about variance. But like something like retrace would have just like cut that trace completely and not learned from it. So this is sort of what we think is the source of this like better sample efficiency, is by like remembering these trajectories with a small importance sampling product. Sorry, let me check the time for a second. Yeah, so we're running low on time. So I don't want to spend a lot of time on the implementation, but you can actually implement this almost exactly like the eligibility trace we saw before. The difference is that you need a few traces to sort of separately remember like the gamma and lambda discounts and keep track of like your beta value. And but otherwise, like this is exactly the same as TD lambda that I showed you before. And the reason this is just an approximation is because if you don't revisit a state in the trajectory, then this is exactly correct. Like this gives you the exact algorithm. But when you do revisit, you start getting a weird effect of like you're taking the min of a sum instead of the sum of a min. So like it's not exactly the same. So this isn't exactly how we implemented it in our paper. We did sort of the more theoretical correct thing where you count duplicate state action pairs as being distinct instances. But even if you do this, since you're always just multiplying by row and then taking the min, this should also be convergent. So this is actually something I realized after finishing the papers. Like there are like these online implementations of these seemingly offline methods, which is pretty cool. But if you're doing experience replay or you have a short episodic task, you can also just do that. Okay. Yeah, so let me show you the domain first. So to test this hypothesis of sort of better credit assignment and longer term credit assignment, we created this bifurcated grid world environment. So the agent starts at S here and it's trying to get to G, and one of the paths is clearly shorter than the other. So when this is discounted, like the optimal path is to go right and like the bottom right path. And what's interesting about this bifurcation structure is at B, the action that's taken pretty much determines like the ultimate outcome of the episode. Like unless the agent doubles back on itself, like that one action at B is really important. And it's in a sense, it sort of amplifies this credit assignment problem of like, if you just fail to have the correct action in your policy at B, just like you're not going to do that well, despite how simple this environment is. Like it's a deterministic grid world, but just like it's really important to have that one action correct. So what we did then is we train 4 of these methods. You know, RBIS is ours, and then we also have retrace, the truncated IS, and then recursive retrace. I didn't have time to explain, but it's sort of like an adaptive retrace, basically. And what we did is we have it's an off policy task. We're doing epsilon greedy control, and we explore for a few episodes, and then the agent starts exploiting its policy, and it's learning. It's trying to predict a slightly greedier policy than it's actually executing. So like the epsilon for the target policy is lower than the behavior policy. And we try a bunch of learning rates, like step size parameters, those alpha values, and we sweep lambda, and then we take the best. We take the area under the learning curve. So like each point on this graph is a learning curve, and the area under the curve is sort of representative of how fast that agent learned. And then we're plotting it over lambda. And what we find is it's the findings were pretty interesting. That like the original hypothesis of faster learning is slightly correct, but mostly in the like lower lambda regime, like when lambda is less than 0.5. But it's not like a huge difference. I think what's more noticeable about this graph is that we have a more robust algorithm in a sense to lambda. So I think like what ended up being the main benefit was that there's actually just a broader range of lambdas that you can use with RBIS that gives you strong performance. And this is evident. We tried some more grid worlds, like some more complicated ones with more bifurcations like this one. And it starts like exaggerating the results. Like you can see even now, like almost up to maybe like 0.8, 0.9 lambdas, like the RBIS is performing much better than the other baselines. And so I think this makes sense because we're preserving these eligibilities. It's able to remember how much credit it's sort of already assigned to these state action pairs. And when it starts getting too small, it tries to stop clipping those eligibilities. And so it just makes it learn a little bit faster, like on those trajectories that something like retrace just wouldn't be assigning credit to. And I think like, when lambda's small and it's like cutting the trace a lot, then like there's an even larger benefit. But as lambda gets closer to 1, then it starts resembling more like gets closer and closer to important sampling. So that's why like these methods, like particularly truncated IS, just starts to fail. We think that's due to that divergence issue that I was talking about before. So it was interesting, to see that reflected in the empirical results as well. Question?
So by the same logic, doesn't it seem that for a smaller lambda, maybe there's more clipping that could potentially be done because there's something with lambda to the k, and but that's not what we see, right? So do you have any thoughts on what might be happening?
Yeah, that's a good question. Yeah, thanks. So the question was, when lambda is small, like close to the left side of the graph, where we have this exponential decay, so we're actually cutting the trace more, like all the methods are cutting it much more. And so why do we think that there's this performance gap? I think what it is if you actually, again, what you see, if we go back to sort of the comparison of these different trajectory aware methods, a lot of these methods, like for example, truncated IS here, it's unconditionally cutting this trace by multiplying by lambda to the k. But and similarly with recursive retrace, because it's multiplying by lambda. So whenever you have this multiplication of lambda, it's sort of saying like, in addition to how much I'm cutting the importance sampling product, I'm also just going to decay it by this really small number, because like if lambda is close to 0, it's just decaying it a lot. And that was one reason we put the lambda inside the min here, because even if lambda is small, it's not taking the product of two small numbers. It's just taking the min of two small numbers. So it tends to be larger. So it's like, it's in a way, it's surprising that a small lambda, you'd still see a difference. But I think this is why. It's just because in a sense, you're almost like squaring this small number, which is already really small. And so it just makes it virtually zero. And then these other methods are not really learning from those experiences. But that's a great question. Yeah. Yeah. And I think, you know, like we have a couple more grid worlds, but like ultimately the results qualitatively are almost the same. So that was nice to see that like there was some consistency, like despite changing these topologies quite a bit. Here we have 3 goal states. And in this one, we have this like very kind of interesting, like multi-path, but similar bifurcation. And we also get similar results here. So this was a very interesting proof of concept of kind of like one way we think trajectory awareness could be practically useful. And then, of course, in addition to that, we've unified a lot of this previous work and proved convergence conditions. We showed that truncated IS, which a lot of people do, just clipping this important sampling product, is actually not necessarily good, and you should be using other methods. And yeah, and it seems like, you know, trajectory awareness is really important when you have these few critical actions that largely determine the outcome of your agent's performance. And yeah, more details are in the archive paper. You can find it online, and I'll be presenting this at ICML, like Marla said. And thank you all for listening. Yeah. Okay, question?
Yeah, you mentioned in the beginning some like connections to maybe using eligibility traces and like replay buffers or something like that.
Yeah.
Did you guys explore a little bit like the function approximation setting? Or there's like benefits or pitfalls that direction?
Yeah, that's a great question. So the question was essentially at the beginning, we mentioned the possibility of replay buffers, which are commonly used with function approximation, like neural networks. Did we explore that? I think like ultimately we didn't really explore it. So I think as this work evolved, like when I was talking about the pseudocode here, like I said, this is not found in the paper because like I didn't realize it until really until recently that there could actually be like online approximations to these methods. And so at least in terms of linear functions, like we just didn't even try that. We were just kind of like, we wanted to just see like theoretically tabular setting, like, can you do better? Because in a way, like if you can do better in the tabular setting, then like future work, there should be approximations or ways to get it to work with linear functions. For the replay buffers, like you're asking about, with like DeepRL, we didn't really try that, but that is sort of something I want to try soon, I think. Like that really was one of my main motivations of this, is because like that, even when doing something like just regular lambda returns with DeepRL, or even n-step returns, like a lot of times you just have to do it like offline in this trajectory. So like it seems like an appropriate setting. So but yeah, I guess long answer to short question. We didn't really try it yet. Yeah.
So maybe a related question. So about the theory itself, do you think there's a relatively easy extension to the linear setting, at least to like the theoretical results, as to if we do the clipping in this particular fashion, we still have those sort of convergence results, because that would be really neat.
Yeah, so the question was, does this theory that we derived, could it potentially apply to the linear function approximation setting? I have to think about that. So I think like my concern is that there's always the deadly triad issue of like you're bootstrapping, it's off policy. So So yeah, like my intuition is that there could be like some problem with linear function approximation. Like you would, my guess is that you would probably still need like, you know, gradient TD methods or something to make it actually stable and convergent. But yeah, that's just me being cautious. I think like it would be very cool if it converges, but like, you know, I'm not even sure that does like regular off policy importance sampling, like I don't think it converges. Yeah, so I think my guess is that then clipping those traces would just make it worse probably. Like, so you'd probably need gradient TD or something. Yeah.
Okay, so just as a reminder, do you can you remind me if retrace and all those results are in the linear settings, or are they also tabular?
Those were also tabular theory, I think. Yeah, I think there were some later papers that tried to extend them to linear functions. And like I said, I assume they probably did something like gradient TD or some sort of like stochastic gradient descent to like make it convergent. Yeah, because I think if you just tried to like do the online TD method, then it would probably not work. Yeah. So yeah, great question again. Yeah. I think I see something in the chat here. Okay, cool. Just making sure. Sweet. Any other questions that you have? Awesome. Well, yeah, I'll be around if people want to talk one-on-one afterwards. But otherwise, thank you very much for coming.